Put it that way, okay? Whatever you do is better than 0. And I may or may not count off for it, okay? So just these things happen. All right. Today, the good thing about today, people, is it's the last new thing before the test, okay? Yes, ma'am. Oh, you just, whoop, whoop. Okay, happy. Very good. This is the last thing, new thing before the test. So that's the good thing about today. All right, but we've got to stay a little bit focused to get with it here. Okay, let's briefly talk about Friday. On Friday, we talked about infinite limits. And that was just limits that go to infinity, or limits that went to negative infinity. These are things where we've got infinite limits. Now, remember, the big thing that we tied together Friday was that we might ask that question, or that really tells us a lot more than just infinite limits. If you know that a limit is going to infinity, what else do you know? If a limit is infinity, it tells us other things about it. What else does it tell us? Vertical asymptote. Okay? So if we know that we have a vertical asymptote, we know we've got a limit of infinity. If we know we've got a limit of infinity, we know we've got a vertical asymptote. And both of those are kind of things that we had already tied together. There was one other thing that we tied in there. Who can remember what else that we tied into that? It's a non-removable jump. That's another thing. Again, it's kind of something that we already knew, but it's something that is at the same time new to us here. There was something else, so something that was non-calculusy, and this was the one that.
Could it be like that the function is going to be a positive number, like both positives? I remember there was like if it's positive and then negative, then it does not exist. If they're both positive, and it's positive.
All right, that's close to it because you said both of them. If we've got limits at it, we've got a limit of infinity, we've got a vertical asymptote, we've got a non-removable jump, we've got a fraction, okay, because that's the only way we can have both of them to talk about. And what's special about the fraction at that vertical asymptote? Who remembers that? It's going to be undefined. The denominator equals 0 and what? And the numerator is not 0. Okay? Those are things, so we tied all those together and said, if we've got one of those, we've got all of those. Okay? If we've got a fraction that the denominator is 0 and the numerator is not a 0, then we know it's a vertical asymptote. We know that the limit's going to be infinity or negative infinity here. It could be infinity, it could be negative infinity. Either one of those. We know it's going to be one of those two. All right? It might be infinity on one side, it might be negative infinity on the other side. But we know the graph's going to have to look something like this stuff right here. Something like that. All right? To me, this is the trickiest part, and in looking at some of your homework, this is what confused you, or not confused you, but this is what stumbled up a couple of you. What happens if the denominator is 0 and the numerator is 0 at a point? That gives us indeterminate form, okay? So when we've got the numerator equal to 0 and the denominator equals 0, that gives us indeterminate form. Oops, indeterminate form. So what does that mean we need to do? We need to do some factoring. We need to do some simplifying, which is usually going to be factoring. Okay? And if it's indeterminate form at that place, if we need to do some factoring at that place, then it's not going to be a vertical asymptote. It's not going to have a limit of infinity. It's not a fraction where the numerator is not 0 and the denominator is. what normally happens at a place like that? What do we have going on? We have a hole. Okay? We normally have a hole. That normally winds up being a hole in your graph. Okay, so if both numerator and denominator are 0, we expect there to be a hole in the graph. If just the denominator is 0, that's when we expect the limit to be infinity or negative infinity, or does not exist because it's infinity on one side and negative infinity on the other side. Okay? So that's kind of reviewing what limits, what infinite limits are. Okay? All of the limits that we looked at on Friday, we were always going to a specific point. We'd go to x approaches 3, or x approaches 3 from the right, or x approaches 5 from the left, or something like that. Today, in our final talk, we're going to talk about limits that look like this. Right here on the first page of 06. The limit as n approaches infinity. Okay? The limit as n approaches infinity. And if you look, I've got, well, let's do this first one together, okay? Introduction to limits at infinity. I want you to fill in the chart here. Use your calculator. Fill in the chart, or you may not even need your calculator. You may be able to look at that and tell me, and give me your best guess at what the limit's going to be. Give you a couple of minutes, see if you can figure out something. Give you 1 minute, 45 seconds. This is going back to kind of where we were to begin with. Putting numbers in and see what we get out, and then make an interpretation based on the numbers. Now when you punch that on your calculator, I bet you're going to get something like this, aren't you? 1e negative 04. If you're remember that this means the same thing as 1 times 10 to the negative 4. That means I've got a 1, and I'm going to move the decimal back 4 times. 1, 2, 3, 4. So I have a decimal, 3 zeros, and 1. 1e to the negative 4 is 0.001, which I think is the right answer. I think that's the right answer for this one here. Are those the answers y'all were getting? 0.001? 0.00001? Then something like that. What do you think it's going to?
Negative infinity.
Negative infinity? Okay. Anybody say something different? He says negative infinity. 0. Are they the same place? No. Nah. You sound discouraged.
Well, because it gets smaller and smaller, it's approaching 0. I was getting excited about all the negatives.
Yeah. So, but it's getting smaller and smaller. I agree with that. But what is it really getting closer and closer to? Negative infinity, but would be what kind of a number? Negative 10 million, negative 12 million, negative 2 trillion. This is just getting really, really smaller and smaller. If you put this one in, you'll get another 0 on there. 1, 2, 3, 4, 5, 6, 0. What do you think, if I had a 1 and 20 zeros, what do you think it would be when I divided? 0.20 zeros and 1. So what am I getting closer and closer to? 0. I'm getting closer and closer to 0 here. Okay? So this is becoming closer and closer to 0. The limit of anything that looks like this, 1 over n, is 0. What if it's 2 over n? What do you think it'll be? 0. What if it's 1,000,000 over n? So it doesn't matter what's on the top? Josh just said that. Are all y'all agreeing with it?
Yes.
Yes, because it doesn't matter what the top is. The bottom, when we are approaching infinity, the bottom is just getting massively larger and larger and larger. And it doesn't matter what's on the top. It's just going to wind up being 0. So it's going to be approaching 0. So if you have anything, 7 over n, 7 over x 11 over x. Negative, ooh, what about negative 12 over x? What's it approaching?
It's still 0.
Very good. She's so confident in her answers. Yes, it's still 0 because it'd be negative 12 divided by 10 million. Well, that's still a really small number. It's just got a negative sign in front of it. So it's still 0. It's still approaching. It would just be approaching from below the x-axis instead of above the x-axis, okay? So anytime we've got something that looks like this, 1 over n, it's going to approach 0, okay? And this is called a limit at infinity because we're approaching infinity with it, okay? Now, so I want you to take this same type thing that we just did, and I've got 3 problems for us here. And I want to take 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think there's 12 of y'all, okay? So 1, 2, 3, Nick, you 4 solve this first problem that's on slide 2 for y'all. That's 2x squared plus 3 over 5x minus 7. Y'all are charged with finding us an answer for that, okay? All right. 1, 2, 3, 4. Ladies team, y'all are charged with getting the second problem. 2x squared plus 3 over 5x squared minus 7. And men, I'm counting on you, okay? You men, you have the last problem. You have the last one, 2x plus 3 over 5x squared minus 7. So, y'all put your heads together, come up with solutions for us here, okay? Give you about 3 minutes to come up with the solutions to these 3 problems. Yep, 1, 2, 3. Be sure you're working the right problem. Y'all are working slide 2, y'all are working slide 3, and men folks, y'all are working slide 4 over here, okay? How about that? We have a girls and boys team, a girls team, and a boys team. Wow. All right.
The first one is like 4.5.
What did that say? That's where we're going to be.
I like hearing you say 0.
Be careful putting these in your calculator now. The numerator needs to be in a parentheses and the denominator needs to be in a parentheses. First one was squared on top.
Yeah, I got
Okay. All right, group 1. What kind of solution are y'all coming up with?
Keeps getting bigger.
Oh, it keeps getting bigger. What about group 2?
Stays at 0.4.
Oh my goodness. It stays at... Ooh, y'all better come together, ladies. Come on now. Woman power depends on you 4, okay? Now, come on. All right, man. Don't let me down back here now. What do y'all think, man?
I think it's approaching 0.
Okay. All right. Yes, ma'am. Ladies, when y'all come up with a solution that y'all are going to stand on, somebody go write all the stuff on the board, okay? Gentlemen, when y'all come to a solution that you're going to stand on, please go write it on the board and tell us what your answer is.
Hey, they're giving up free food, let me tell you.
Yeah.
I see what I did on that homework last night. You asked me either or, and I put vertical isotope and removable.
Yep.
Yeah. I don't know why.
Yeah, just I understand that happens sometimes.
Oh wow. Just a straight line.
All right, problem number 1 has been answered. Problem number 2. Ladies, did y'all come to an agreement? All right, somebody be brave and go write it on the board then. Yes, you. Gentlemen, y'all ready? All right. Yes, you may. All right. And gentlemen, we're ready for you. All right. Jerry is the designated writer. All right, I like this. All right. All right. So we came up, and all of you came up with totally different answers. Well, each group came up with very similar problems, but totally different answers. And we need to kind of come to some conclusion of do we think we're in the right ballpark with any of them here. I've rewritten these 3 problems over here, and I'm just going to transfer your final answers over here. You said that was infinity. You said that was 4/10, and you said that was 0. Now, as you look at those 3 problems and those answers, can you come up with some logic of why that's true? The square changes the answer. Okay.
If the square root on the top, it's going to be...
A square, you mean, not square root.
Or, oh, excuse me, so square on the top, and it's going to be larger than it would be a square on the top and the bottom. And if you have a square on the bottom, it's going to be smaller than the half one.
Okay? So we're trying to take what we've learned. We're always looking for shortcuts. Have y'all noticed that? We're in math. We're always looking for an easy way to do things. So, now, here's what I hear from Sutton. The squared's on the top, and then this is going to infinity. Both of them had a squared, and it was going somewhere else. The square was on the bottom, and it's going to 0. What do y'all think? Think it's a coincidence? Okay. Let's think about this. Tell me what's happening to the bottom when I put big numbers in there. It's getting big, right? What's happening to the top, though, when I put that same big number in there? It's getting bigger than that, right? Would you agree? No matter what number I put in the bottom, if I put a bajillion in here, I'm going to get a bajillion squared when I put it in up top, right? That's definitely going to be bigger. So does it make sense then that this is going to be getting bigger No matter what number I put in as I'm going to infinity, the top's going to be getting bigger faster than the bottom, so then it's got to be going to infinity. It's never going to get to a point that it just starts going down. All right, let's look at this last one over here. The bottom is going to be getting bigger faster than the top is now. Would you agree with that? If I put a bajillion up here, I get 2 bajillions, but down here I get 5 bajillions squared. That's a lot bigger number, whatever a bajillion is, okay? So the bottom is getting much bigger, much faster, so this has got to get down, got to be approaching 0. It's going to be getting closer and closer to 0. Now, not negative infinity? That's a good question. Why is it not negative infinity? It's a fraction. The bottom is, yeah, it can't, the bottom's getting really big, so it's got to be getting down close to 0. It's not just bottoming out. Now, this one in the middle, that one kind of bothers me a little bit. Because both the top and the bottom are getting big, aren't they? Getting big at the same rate. Well, where'd that 4/10 come from then? You got an answer? Where'd you get 2 and 5 from? Oh, well, Sue, explain to us then. Ah, she's throwing you under the bus now, Sue. Where'd you get 2 and 5 from? Why is it 2 and 5? Why isn't it 3 and 7? Or why is it 2 and 5, y'all think? So, all right, let me hear what are you telling me then, if you were looking at this problem here, 3x squared plus 7 over 11x squared minus 9, what do you think the answer would be then? 3 over 11. Why do you think that's going to happen? Thank you, sir. Thank you, sir. Did y'all hear that? When we put $1 million in here, all right, think about it. You got $1 million. You square that $1 million. Now you got, I don't know, a bunch of money, okay? Do you really care if somebody adds $7 to your pot? Does it really make any difference to add $7? No, it doesn't. Not whatsoever. Same thing down here. If you got $1 million squared, if somebody, are you going to worry about somebody stealing $9 out of your pocket there? Probably not, okay? Now, if they got 9 million, okay, that might be getting enough to worry about. But no matter what size this number is here, this 7 and this 9, when we're approaching infinity, those numbers don't matter. They're not going to make any difference in the whole big deal. So, all this to be concerned with is what's happening with this one here, the x squared ones. Okay? And since there's a 3 in the front of since a 3 is the lead coefficient in the numerator and 11 is the lead coefficient in the denominator, that limit's going to be 3 11ths. Okay? Now you can work it out. You can do it graphically or numerically just like we did before, and you'll find that it gets to be closer and closer to 3 11ths when you get to large enough numbers. All right, y'all seem to think you're smart people, so I want to give you 3 other problems then. What about this? The limit as x approaches infinity of 5x cubed plus 9 over 7x squared minus 5. The limit as x approaches infinity of 5x cubed plus 9 over 7x cubed minus 5, and the limit as x approaches infinity of 5x squared plus 9 over 7x cubed minus 5. Now see if you can use some of the same things that you were just telling me about and come up with solutions to these without doing anything other than thinking. Can you just think about this? If you can't think about it, plug some numbers in and see if you can come up with something. What are you thinking? The difference is, all right, well, what if it's 7x on the bottom? still be infinity?
Because the top would be a lot bigger.
So you think if it's 5x cubed plus 9 over 7x or 7x squared, both of those you think is going to be infinity?
Yes.
Does this side of the room think that? Okay. You're on both sides. Oh, you're on both sides. Okay. So infinity we think would be the limit for that. Because the top, since that exponent's bigger than that one's going to be getting bigger faster than the denominator, so it's going to be increasing without bound. Well, what about the middle one? 5 over 7. Okay? Why do you think it's 5 over 7? The plus 9 and minus 5 are immaterial. Both of these are the same, aren't they? X cubed and x cubed, that means they're getting big at the same time, so 5 over 7. Well, what about the last one then? 0. Why 0? Because the bottom's getting bigger, so we're going to be bottoming out at 0. Yes, sir?
So if it was like, in order to get negative infinity, it'd be the first one, so like 5x cubed plus 9 over 7x squared minus 5. There'd have to be a negative in front of either the 5 or the 7, right?
Very good. Very good. So, now, looking at these 6 examples, I hope is enough for you to understand that we just solved a bunch of problems with 3 rules, okay? Do y'all like rules in math? If it's like this, you do this. If it's like this, you do this. Okay, that's where we're at here, okay? So if you'll go over a couple of slides to here, you'll see the 3 rules that apply with limits at infinity. Okay? Limits at infinity. When x is going to infinity, okay? When x is going to infinity, you need to look at the degree of the numerator and the degree of the denominator. What do I mean by degree? The highest exponent, okay? The highest exponent. Let's look at this problem. We didn't look at one like this. Limit as x approaches infinity of 3x squared plus 5x minus 9 over 7x minus 5. Okay? Now, when you look at that, look at the numerator. The degree of the numerator is 2. The degree of the denominator is 1. Because the highest exponent up here is 2. It's not adding up all the exponents. It's the highest exponent is 2. The highest exponent in the denominator is 1. So now we are going to look at these 3 rules. If the largest number, if the largest number is on the top, then the limit is either negative infinity or positive infinity. I know I'm working from the bottom here, but that's because of the example that I used there. If the degree of the numerator is greater than the degree of the denominator. Yes, ma'am? Very good question. That's what we're about to talk about here, okay? Look at where we're going to. We're going to infinity. So this is a positive number, right? If I take a positive number and square it, what have I got? And if I multiply it by 3, what have I got? I've got positive numbers everywhere. What if it's a positive number times 7? What am I going to have? Positive number. If I subtract 5, is it still going to be positive? Yeah. So positive divided by positive, the answer is going to be positive infinity. Okay? If, let's say we change this problem. What if we had the limit as x approaches infinity of 3x squared plus 5x minus 9 over negative 7x minus 5? Plus, doesn't matter. See, now the numerator is going to be positive, but the denominator is going to be negative, isn't it? So this one would be going to negative infinity. Okay? So, if the degree in the top is larger, numerator is larger, we're going to infinity. If the denominator is larger, we're going to 0. If they're the same, it's the lead coefficient over the lead coefficient. This is the lead coefficient. The lead coefficient is not the first one. The lead coefficient is the one with the highest degree. So if I turn this around and make it negative 5 plus 7x, the lead coefficient is still 7 here, okay? It's the one that goes with the highest degree. And you memorize those 3 rules, and you are a long ways towards solving any problems dealing with limits at infinity. Okay? Here's a big thing that I always recommend that you do. No matter what, always test the limits numerically. I don't mean test them with a bunch of numbers. I would just test it with 1 or 2 really big numbers, and that's mainly to determine the positiveness and negativeness of it. Is it positive infinity? Is it negative infinity? Okay? Any questions so far? Good. Look at these 2 limits here on the next slide and determine what you think the answers to be. I'll give you 2 minutes. Go. Huh? The first one, that's just the, I don't know why I put the function over there. Oh, I said graph f of x. So you could graph it and then evaluate the limit. Is what I was saying. But don't worry about graphing. I really want you to be able to look at that without graphing it and tell me what the limit is. I would use my rules, and then I would go back and check it with my negative, with numbers that are either approaching infinity or approaching negative infinity, and see if it makes a difference in my answer. Oh? Yes. This second one's got a negative in front of the infinity there, people. Yep. It's very hard to see that, I know. What do we come up with? Terry, do you have an answer for us for either one of these? Tell me what the answer is. This one is just infinity. Okay? Is what? It's 0. Okay? Okay? What? Do y'all disagree? I don't know. I just wrote down what the man said here, okay? I'm not saying he's right or wrong on either one of them there, okay? Sutton, you said?
Your degree, the highest degree on the last one is 2, and the highest degree on the bottom is 1. It equals infinity, but you have to remember, so we're going to negative infinity. So you have to plug in a negative. And so a negative times a negative equal positive, so x squared is positive up top. And since x is just by itself, it'd be negative. So you have a positive up top and then a negative below. So negative infinity.
So you think it should be negative infinity?
Yes, sir.
Okay.
Oh, yeah, that's right.
Okay. Are you changing just because Sutton said it, or you really believe it? Oh, Sutton's always right. Okay. Ah. Okay. So, infinity and negative infinity, okay? How many think these are the 2 right answers? There you go. Okay. And Sue is just so engrossed she doesn't know. Okay. Infinity and negative infinity are correct there, okay? That is correct. Because looking at our rules here, the highest exponent is in the numerator, so we expect it to be going to infinity or negative infinity. Okay? If we look at positive numbers, the numerator is always going to be positive, the denominator is always going to be positive, so it's going to positive. When we're looking at negative numbers, the numerator is still going to be positive. Now what about this negative 8x? It doesn't matter because remember, we're not talking about 1, 2, 3, 4, 5. We're talking about negative 10 million. We're talking about numbers that are way out there somewhere. So we're talking about really large numbers in magnitude. So the only thing that we need to be concerned with is this first term here. The top one's always going to be positive, even going to negative infinity. The bottom one's always going to be negative, going to negative infinity. And a positive divided by a negative will give us negative infinity. Okay? Now, let me ask you something. What does this one right here tell you about the graph of this function? The limit as x approaches infinity is infinity. What does that mean?
Like that.
As we get further out here in this direction, in the right direction, x becoming greater than infinity, this function is approaching infinity, so we expect this function to go up out here to the rightmost end. Now, I have no idea what it does in here. We'll worry about that later. But we expect it to go up. What does the second one tell us that we expect to happen? Going to negative infinity. Going down. Where is it going down at? Way over here. We expect it to be going to negative infinity because, remember, this is positive infinity in the x direction. This is negative infinity in the x direction, okay? So limits at infinity, this is one of those things that you want to kind of store away. Limits at infinity tell us what's happening at the end of the graph. Now, there is no end to the graph, okay? But it tells us this is its behavior at the end of the graph out there, okay? What did I just say?
The limit's just, if the limit is approaching infinity, it's just towards the end, so it doesn't account for the meat or the middle of the.
That's right. We don't know what's happening in the middle, but we know what's happening at the end of the graph, right? Solve the problem. We need some music to play in here, don't we? Yes, we need some nice music to play. That's exactly what we need. Nick, you got us an answer? He says it looks like 0. But that was not a confident 0, that really was. Jerry? Oh, wow. Boy, Jerry's stepping out on a limb there, isn't he? He says he thinks does not exist. We haven't even mentioned does not exist all day long. I don't know. Okay, Jerry, explain to us why you think it does not exist. What does the cosine curve look like, people? It just keeps doing that, right? It keeps going up and down and up and down and up and down. It just always goes up to 1, always comes down to -1, always goes up to 1, always goes down to -1, right? So what's it approaching out there? It's going between 1 and -1, isn't it? I don't care what number you tell me to find the cosine of 2 trillion, but the cosine of 2 trillion and 1 is going to be different. It's never approaching a single number. It's just rocking the boat. All it's doing is rocking the boat all the time. It's just going up and down. So the correct answer is does not exist. Good job, Jerry. Good job. All right. It doesn't exist. What's the limit as x approaches infinity of sine of 0? Of sine, I mean. Does not exist because it's just going to keep going up and down, up and down, up and down. Right? All right. Now, see if you can hit the knuckle curve then. See if you can hit the knuckle curve. And when you graph that one, it's going to make your head hurt, okay? But so then you're going to look at the table set and you're going to say, this can't be right. So then you got to go back and use just good old brain power. Ooh, Jamie's turning up her nose at it. Does it look that ugly? Don't like it. Jonah's awful quiet back to here, though. He's working. He's coming to a solution there. Oh, my goodness. Look at there. What do we come up with, people?
I drafted it and it looked scary. So
It looked scary, so you gave up? Oh my goodness, what on earth? Well, in perusing around the room, I saw this written down on 2 papers. And the rest of you, I didn't really see anything written down. You're just looking at the graph, which is okay. So, Josh, you had that written down. Explain why you think that's the correct answer.
All right, so if just cosine of x is going to be between 1 and negative 1, and it's never going to be between 1 and negative 1, but the x on the bottom is continually getting bigger, then the total number is going to continually get smaller, and eventually get to 0.
Okay? Y'all agree with that? Or y'all just shaking your head so hopefully he'll move on to the next problem?
a little bit of both.
When I plugged it in, I got positive, negative, negative, positive, positive, negative, negative.
Okay? If you look at because this is where I said if you start looking at it numerically, you really get confused here. Because looking at it numerically, yes, those numbers, they'll be positive for a little while, then they'll turn negative for a little while, and every now and then you'll even get a 0 in there. Okay? But now, here's why. Just what Josh said. The top is never bigger than 1. The top is never smaller than negative 1. Okay? So think the top is just going back and forth between 1, negative 1, floating through 0, back and forth. But the bottom's getting to be a really big number all the time. It's continuously getting larger and larger. So if you could actually look at this graph, here's what you would see. It's going to start off up here nice like that, and then it's going to get lower and lower and lower and lower and lower, and it just gets smaller and smaller until when you get out here far enough, all it's doing is just barely wiggling up and down. But guess what? It never stops. It's going to continuously keep going up and down, up and down, up and down, slightly above the x-axis, slightly below, all the time. Your calculator will eventually get to the point that it just flatlines. If you do a numerical, the table will eventually get to where it's just flatlined to zeros. But that graph's never going to sit still at 0. It's always going to keep getting larger and smaller and smaller and smaller, approaching 0 all the time. Every now and then it's going to go through 0, but it's always going to keep going back and forth, back and forth, back and forth. That's a very interesting problem there. But do you see with all of these, you need to look at, you've got to know your 3 rules, but then you also need to be able to look at them separately. Look at what's happening in the numerator, look at what's happening in the denominator. All right? Actually, there's really not a rule you could use. Well, there's the degree of the denominator is 1. You don't have an x in the numerator. You have a cosine of x. You don't have an x, so it's really hard to say there, okay? Well, let's do something that I know y'all have been dying to do. Yes, ma'am? Why? Okay, good question. All right? She says, why is this does not exist? Because the limit for the numerator is does not exist. The limit for the denominator is infinity. Why is that just does not exist? Because if you look at it graphically, Yiming and Long, that graph is getting closer and closer to 0 out here far enough. If we can get out here far enough on it, that graph is just barely moving up and down, and it's honing in on 0 all the time. It's getting closer and closer to it because the distances are getting shorter and shorter. The distance up and down is getting smaller and smaller. think of a spring. If you put a weight on a spring and pull it down and let go, what's going to happen? It's going to come back up, and then what's it going to do? Go back down, up, down, up, down, up, down. But unless something acts on it, like the friction in the room, like the friction, that would stay bouncing forever. Okay? For example, I mean, think of it this way. If I'm going to walk to the wall, and I'm going halfway to the wall every time, I'll never get to the wall. Because I've gone halfway. Well, this is halfway. Well, this is halfway. And physically, I will get to a point that I can't move any. But actually, if there wasn't space, if I wasn't taking up space, if the wall wasn't taking up space, I could never get there by going halfway each time. Same thing, same type principle applies here. It keeps going up and down ever so small that our minds and our calculators and all the devices we get says it eventually has to get to 0. But it's never going to get to 0 because no matter what number I give you, if I go one further, it's going to be just positive. And if I go enough further, it'll go back to negative.
But it touches 0.
It does. Very good. And that's really confusing, isn't it? Because it keeps crossing over 0. It crosses over 0 and then comes back up to 0 and crosses over. But all the time, every time it goes below, when it goes back up, it doesn't go quite as high. When it goes down below, it doesn't go quite as low. It just keeps getting closer and closer all the time. So it's just, it just keeps getting a smaller bounce every single time.
Like when it's just regular, like this cosine x, like it's too uniform.
That's right. It's very uniform. It's always moving in the same pattern. But when you divide it by x, suddenly you've made it, instead of going up and down the same amount every time, we're making smaller the amount we're going each time. Well, now let's do something I know you've been dying to do, and that's a word problem. Okay? All right, let's look at this problem here. Suppose that f of t measures the level of oxygen in a pond where f of t equals 1 is the normal unpolluted level. Okay? And t is measured in weeks. When t equals 0, organic waste is dumped in the pond and the waste material oxidizes. The level of oxygen in the pond is found by the following function. What does that mean? Okay? You've got a pond, and when we start the clock at t equals 0, something gets dumped into the pond that's going to make it contaminated water. So we can't use it. All right? So, the problem I want us to focus on in right now is B part. What is the limit as t approaches infinity? What is the limit as t approaches infinity of f of t? Who can tell me? 1. Okay? Now, here's a mind-blowing moment for you here. Will it ever get to 1?
No.
No? Why not?
Well, for one, there's the insignificant numbers behind it that'll kind of slightly skew it.
Okay? This minus 3t, mathematically, no matter how much I put in here, I got to subtract 3t amount of that out in the numerator. And on the bottom, I don't have to subtract that out. So I'm never going to get to 100% pure oxygen again. Never get to that level. That's mathematically. What about real life?
It's not going to sit there forever.
Yeah, I mean, something else is going to go back into that water and contaminate it there. But this is just a quick example. We'll look at the other parts some other time, but y'all are smart people. I think y'all could do them without us here. But this is what I wanted to show you. We are actually going to tie this stuff to things that you've already done in classes before. We're going to tie it to real life problems, okay? We're going to go across the hall, and y'all will have a chance to work next. Thank y'all.